Hello friends, I am Adeesh Deshpande from Fergusson College. We are discussing ionic equilibrium where we completed the discussion of conceptual theories of acids and bases. So let us switch over to the next part of the chapter. Now let us consider dissociation of acids and bases. So acids and bases are classified on the basis of their extent of dissociation. So in terms of degree of dissociation, that is alpha, earlier we studied this term. So if degree of dissociation of acid is quite large, then it is called as a strong acid or strong base. And if this alpha of acid or base is small, then it is called as weak acid or weak base. Now, strong acids are those which dissociate almost completely in their aqueous solutions and give large number of H plus ions in the solution. So, almost complete dissociation. So, here are the examples of strong acids: HCl, hydrochloric acid, H2SO4, sulfuric acid, HNO3, nitric acid. So, these acids, whenever dissolved in water, they almost dissociate completely, producing large number of H plus ions. So H plus ion, so it is called as strong acid. Similarly, partial or incomplete dissociation is observed in case of weak acids because reaction is reversible and reaction is not complete. So molecular concentration is high, thereby H plus ion concentration is small. So such acids are weak acids. So weak acids are those which dissociate to a small extent in their aqueous solutions and give less number of H plus ions in the solution. Examples are given: acetic acid, carbonic acid, hydrocyanic acid, etc. Like acids, we can classify bases also as strong bases and weak bases. Strong bases are those which dissociate almost completely in their aqueous solutions and give large number of OH minus ions now in the solution. So almost complete dissociation. Examples are NaOH, KOH, that is sodium hydroxide, potassium hydroxide. Similarly, weak bases are those which dissociate to a small extent in their aqueous solutions and give less number of OH minus ions in the solution. So partial or incomplete dissociation. Examples are ammonium hydroxide, magnesium hydroxide, etc. So in this part of the chapter, students, we only deal with Arrhenius theory of acids and bases because in the laboratory we are going to use almost aqueous solutions everywhere, and so we stick to Arrhenius theory of acids and bases. Now let us find out strength of acid. So consider a dissociation of weak acid Ha in water. There is equilibrium between ions and undissociated molecules of acid. So here is a general weak acid I have taken, Ha. It is dissolved in water. So equilibrium is Ha aqueous reversibly gives H plus aqueous plus A minus aqueous. Now if I apply law of mass action, I will end up with the equilibrium constant, which is equal to Ka. Ka is equal to active mass of H plus into active mass of A minus upon active mass of Ha. So we already studied this last year. General equilibrium constant K. Now in this case, as it is a special case ionic equilibrium and here acid dissociation of acid is considered, so I added that A as the suffix Ka, and the symbol for equilibrium constant is now Ka. Now since again this is a dissociation equilibrium, and so this equilibrium constant is called as dissociation constant of an acid. So if this Ka is large, then that means there is high concentration of ions, H plus and A minus ions, and almost no concentration or negligible concentration of undissociated molecules. And so In that case, acid is strong. But on the contrary, if this Ka is small, this means that there is very few ions H plus and A minus present, but large concentration of undissociated molecules Ha are present. So if Ka is small, acid is considered as weak acid. Similarly, strength of base. Consider now a general weak base as BOH. Let us dissolve that in water and consider that dissociation. So BOH aqueous reversibly gives B plus aqueous plus OH minus aqueous. Now apply law of mass action, you will end up with the equilibrium constant Kb now. It is called as dissociation constant of base. So Kb is equal to active mass of B plus into active mass of OH minus upon active mass of BOH. Now on the similar lines, if Kb is large, ionic concentration is high, base is strong. And if this Kb is small, ionic concentration is less, that is molecular concentration is high, and therefore base is called as weak base. So based on this dissociation constant of weak acid or dissociation constant of weak base, that is Ka and Kb, it is possible to classify acids as strong acids, weak acids, bases as strong bases, weak bases. So what is dissociation constant? It is equilibrium constant at constant temperature when law of mass action is applied to the dissociation equilibrium of weak acid or weak base. So in the earlier two expressions, we did the same thing. Law of mass action we applied to the dissociation equilibrium of weak acid and weak base, and we got equilibrium constant, which is called as dissociation constant of weak acid, that is Ka, and dissociation constant of weak base, that is Kb. Now let us switch over to Oswald's dilution law for weak acid. So this law is applicable for weak electrolytes only, that is for weak acid and for weak base only. Now let us consider first weak acid. What is the statement? The degree of dissociation of weak acid is inversely proportional to the square root of its concentration and is directly proportional to the square root of its dilution. So degree of dissociation of weak acid is alpha. So this alpha is inversely proportional to the square root of its concentration. So alpha proportional to under root 1 upon C as the mathematical form, or is directly proportional to the square root of its dilution. So for dilution, mathematical symbol used is V, that is volume. So alpha proportional to square root of V. So this we are going to prove. So let us consider the derivation. Consider 1 mole of weak acid Ha dissolved in VDM cube of water, and alpha is the degree of dissociation. Then at equilibrium, we can write the equation as Ha aqueous reversibly gives H plus aqueous plus A minus aqueous. Since this is weak acid, there is establishment of equilibrium. Now let's find out the concentrations of these species. Initial concentration. Initial concentration of Ha is 1 mole. With 1 mole we started the dissociation. So initially no ions are present, so 0 concentration of H plus and A minus. Now alpha is the degree of dissociation when equilibrium is attained. So alpha moles out of 1 mole form ions. So according to the equation, it is very clear that when 1 molecule of Ha dissociates, it forms 1 H plus ion and 1 A minus ion. So likewise, if I now consider that alpha is the degree of dissociation, that means alpha moles of Ha dissociate, then they produce alpha H moles of H plus ions and alpha moles of A minus ions. And what is the amount of Ha remain behind? I have to subtract this alpha from the initial concentration, that is 1 mole. And so equilibrium concentrations for HA 1 minus alpha, for H plus ions alpha, and for A minus ions alpha. Now let's find out their active masses. Active masses means concentration in terms of moles per dm cube. Now this concentration is equilibrium concentration. And so divide by the total volume. Total volume taken is V dm cube. And so equilibrium concentration in moles per dm cube for HA is 1 minus alpha upon V, for H plus ions alpha upon V, for A minus ions alpha upon V. Now let us apply law of mass action to calculate the equilibrium constant. So applying law of mass action, you will end up with the expression which is Ka is equal to active mass of H plus into active mass of A minus upon active mass of HA, where Ka is called as dissociation constant of acid. Now from our previous table, let us substitute the values of these active masses. And so what remains? Ka is equal to alpha by V into alpha by V upon 1 minus alpha upon V. Upon simplifying, we will end up with Ka is equal to alpha square upon V into 1 minus alpha. Now if C is the initial concentration of acid in moles per dm cube and V is the volume in decimeter cube per mole, then 1 upon V is called as C, that is concentration. And so I am going to replace 1 upon V in the equation. So I will end up with the expression which is Ka is equal to C alpha square upon 1 minus alpha. Now to make the equation simpler, let us approximate 1 minus alpha to 1. Why I can do this? Because acid is weak acid. So alpha is very less than 1. And so I can consider this denominator 1 minus alpha as simply 1, and we will end up with a very simple expression which is Ka is equal to C alpha square. Now again replace this concentration term by volume. We will end up with one more expression which is Ka is equal to alpha square upon V. So in terms of alpha, it is under root of Ka upon C, or alpha is equal to under root Ka into V. Now this Ka is our constant, that is dissociation constant of acid. So if I remove this Ka from the expression, equality becomes proportionality. And now this is our Oswald's dilution law, alpha proportional to square root of 1 upon C or alpha proportional to square root of V. And so the conclusion is degree of dissociation of weak acid is inversely proportional to the square root of its concentration and is directly proportional to the square root of its dilution. Now one more corollary one has to consider, acidic nature. Now this weak acid solution is considered. So this solution is acidic. It is due to the presence of H plus ions. Now how can you calculate H plus ion concentration according to the table which we already prepared? We will end up with the expression active mass of H plus is equal to alpha upon V. Now 1 upon V is always concentration of weak acid in moles per dm cube. So actual H plus ion concentration can be calculated as C into alpha, but according to the earlier derivation, that is Oswald's dilution law, we saw that alpha is equal to under root Ka upon C. So substituting in this case, active mass of H plus is equal to under root of Ka upon C into C. Now this C I have taken inside, that becomes a square, and finally the expression becomes active mass of H plus is equal to under root Ka into C. So actual concentration of H plus ions can also be calculated in case of weak acid solution using Oswald's dilution law. In the first expression, you will require alpha, that is degree of dissociation. And in the second expression, you require Ka, that is dissociation constant of that weak acid. So with the help of alpha and Ka, you can calculate actual H plus ion concentration. Now let us consider Oswald's dilution law for weak base. Now remember students, if you remember Oswald's dilution law for weak acid, then Oswald's dilution law for weak base is exactly same. The derivation is also same. Only thing different is the species which are considered. So let's consider this. The degree of dissociation of weak base is inversely proportional to the square root of its concentration and is directly proportional to the square root of its dilution. Degree of dissociation of weak base is alpha. So according to the mathematical equation, mathematical relation, alpha proportional to square root of 1 upon C, or alpha proportional to square root of V. So the same relation which we saw for weak acid, now which we are going to consider in case of weak base also. So consider derivation on the same lines. Now let us consider 1 mole of weak base BOH. Now since it is base, we are taking general weak base as BOH. It is dissolved in VDM cube of water. At equilibrium same, alpha is the degree of dissociation. So equilibrium is BOH aqueous reversibly gives B plus aqueous plus OH minus aqueous. Now let us prepare the table to find out their active masses. So initial concentration in moles, 1 mole of BOH is taken. Initial concentration of ions is always 0. Alpha is the degree of dissociation. So equilibrium concentration in moles is 1 minus alpha for BOH, B plus and OH minus ions. Equilibrium concentrations are alpha moles and alpha moles. Let us divide by total volume VDM cube and we will end up with the active masses, that is equilibrium concentrations. So for BOH 1 minus alpha upon V, for B plus ions alpha upon V, for OH minus ions alpha upon V. Let us apply law of mass action to calculate equilibrium constant, that is dissociation constant of base. Expression is Kb is equal to active mass of B plus into active mass of OH minus upon active mass of BOH, where Kb is dissociation constant of a base. Substituting values from the table, we will end up with the same expression. Kb is equal to alpha square upon V into 1 minus alpha. Now replace 1 upon V by C, that is concentration. The expression is Kb is equal to C alpha square upon 1 minus alpha. Now since it is a weak base, alpha is very less than 1. So denominator is approximated to 1 and the expression becomes Kb is equal to C alpha square, or Kb is equal to alpha square upon V, or in terms of alpha, alpha is equal to under root Kb upon C, or alpha is equal to under root Kb into V. Therefore, alpha proportional to square root of 1 upon C, or alpha proportional to square root of V. And so conclusion is same. Degree of dissociation of weak base is inversely proportional to the square root of its concentration and is directly proportional to the square root of its dilution. Now, this solution is alkaline or basic. So alkaline nature or basic nature is due to the presence of OH minus ions. So concentration of OH minus ions can be calculated using the expression as alpha upon V. This we obtained from the table. Now, in terms of alpha, concentration of OH minus ions is calculated as C into alpha. And in terms of dissociation constant of base, active mass of OH minus or equilibrium concentration of OH minus can be calculated as under root Kb into C. Now let's proceed towards numerical problems, that is problems based on Oswald's dilution law. So here are the formulae which I listed over here for weak acid and for weak base. For weak acid, according to Oswald's dilution law, whatever formulae I told you, I have listed over here. Then acidic nature of the solution, that is to find out H plus ion concentration. The two expressions are also given. Similarly, in case of weak base, According to Oswald's dilution law, the formulae are listed, and to find out alkaline nature of the solution, that is to find out concentration of OH minus ions, the two expressions are also given. Now concentrations of H plus and OH minus ions, they are always expressed in moles per liter or moles per dm cube. Now degree of dissociation, the two formulae are already given. Now here are some of the ways of expressing concentrations. Decimolar solution, centimolar solution, semimolar solution. So respective concentrations are given, or yet another way of expressing concentration as m by 10 solution, m by 100 solution. So this is the way how you will obtain concentration in the actual numerical problems. Strong acids dissociate completely in water. Therefore, concentration of H plus ions is concentration of acid. So this point you have to remember. In case of strong acid, H plus ion concentration itself is the given concentration of acid because of complete dissociation. But weak acids do not dissociate completely in water. Therefore, to calculate H plus ion concentration, you have to use Oswald's dilution law and the two formulae which we listed in the earlier slide in terms of alpha and in terms of Ka, how to calculate H plus ions. So those expressions you have to use. Similarly, in case of strong bases, OH minus ion concentration is itself the given concentration of base because complete dissociation again. But in case of weak bases, you have to apply Oswald's dilution law. Then one more term that you have to remember, that is basicity of acid. Basicity of acid is number of replaceable H plus ions per molecule of acid is called as its basicity. So here is the example given. HCl aqueous gives H plus aqueous plus Cl minus aqueous. Now this one molecule with one molecule of HCl, you can replace one H plus ions during neutralization reaction of this acid. And so as during neutralization, per molecule of acid you can replace only one H plus ion. So it is called as basicity of HCl as 1 or monobasic acid. Consider another case, that is case of sulfuric acid. With one molecule of H2SO4, you can replace two H plus ions during neutralization. And so basicity of H2SO4 is 2, it is called as a diabasic acid. So during neutralization reaction of acid, per molecule of acid, how many such H plus ions you can replace to form the corresponding salt, that gives you basicity of the acid. And so number of replaceable H plus ions per molecule of acid is called its basicity. Similarly, what is acidity of base? Number of replaceable OH minus ions per molecule of base is called its acidity. Consider the example, NaOH aqueous. When NaOH is neutralized, per molecule of NaOH, you can replace only one OH minus ions to form corresponding salt. And so acidity of NaOH is 1, that is, it is monoacidic base. Similarly, in case of magnesium hydroxide, with per molecule of MgOH twice, you can replace two OH minus ions to form salt during neutralization. So acidity of magnesium hydroxide is 2, it is a diacidic base. So this is one small part that also must be known because we require this in solving the numericals. Now let's consider the first numerical. A weak monobasic acid is 0.05% dissociated in 0.02 molar solution. Calculate the dissociation constant of acid. So we are given 0.05% alpha and 0.02 molar solution, and we have to calculate its dissociation constant. So percentage dissociation and concentration, they are given to find Ka. Now let's calculate first alpha. Alpha is calculated as percentage alpha upon 100. Substitute. So 0.05 upon 100, so alpha comes out to be 5 into 10 raised to minus 4. Now to calculate Ka, we have to use Oswald's dilution law. Ka is equal to C alpha square. Substitute. So concentration is 2 into 10 raised to minus 2 into 5 into 10 raised to minus 4 the whole square. And so Ka comes out to be 50 into 10 raised to minus 10 or 5 into 10 raised to minus 9. Consider one more problem. Dissociation constant of ammonium hydroxide is 1.8 into 10 raised to minus 5. Calculate its degree of dissociation in 0.01 molar solution. Now dissociation constant is given and we have to calculate alpha. Concentration of base is also given, which is 0.01 molar. So to calculate alpha, use the formula alpha is equal to under root Kb upon C. Kb is given square root of 1.8 into 10 raised to minus 5 upon 1 into 10 raised to minus 2. And so it is square root of 1.8 into 10 raised to minus 3. Adjusting the power of 10, it is square root of 18 into 10 raised to minus 4. So alpha comes out to be 4.242 into 10 raised to minus 2. The next problem, a weak monobasic acid is 12% dissociated in 0.05 molar solution. What is the percentage dissociation in 0.15 molar solution? Now, if alpha 1 and alpha 2 are the values of degree of dissociation of the same acid at two different concentrations, C1 and C2 respectively, then Ka is equal to C1 alpha 1 square is equal to C2 alpha 2 square. Therefore, C1 alpha 1 square is equal to C2 alpha 2 square. Remember, same acid solution is given and two different concentrations are given. So as acid is the same, its Ka is the same because it is a constant for the same acid. And so in one case, that is 0.05 molar solution, 12% dissociation is given. So for 0.15 molar of the same acid solution, what is alpha? This is how you are supposed to find out. Now given is alpha 1, 12 by 100, percentage alpha is given. So calculate its alpha dividing by 100, 0.12. Corresponding concentration is 0.05, C2 is 0.15, alpha 2 you have to calculate. Substituting in the equation, so you will end up with corresponding alpha 2 as 0.0693. Percentage alpha 2 is 6.93%. So students, in this class, we saw dissociation constant of acid and base and Oswald's dilution law for weak acid and weak base. Thank you.